Hello and welcome to this manufacturing process technology part 2 module 38. We were talking about laser machining in the last lecture, and we discussed some basic physical principles behind the light amplification of stimulated emission of radiations. Context of that, we were looking at a pulse Ruby system where we talked about the xenon flash tube and a capacitor circuit which would actually discharge all of a sudden a packet of energy so that the flash tube can get operated, and there is a shiny material on the surface of the flash tube because of which all the energy the light energy is pumped into this ruby crystal in the center right here, and it generates a lasing signal. The signal is basically super focused again with a lens into a small spot size so that there is a hot spot which is created, and there is always a small portion of the material from the surface which is being removed by vaporization and very extremely high speed ablation, because the power densities are very high in this case, almost of the level of about 10 to the power of 7 watt per millimeter square. So a very small fraction of the molten material is vaporized at such a high energy build up at a small spot, and so there would be a substantial mechanical impulse because of such an energy being incorporated in a very small region. So there is a spatter, there is a large portion of the liquid material around which kind of comes out and it is thrown out because of such a high beam power. Since the energy released by the flash tube is much more than the energy generated by the lasing head, therefore the system has to be continuously cooled so that the ruby laser doesn't get so hot that it starts melted, or it starts to melt. So that's how you produce a solid state laser, and you can actually now in detail study the basic physical mechanism behind the laser beam machining process. So it works on the famous Beer's law and the absorption of light. Okay, so machining is normally achieved by the following phases. One is the interaction of the laser beam with the work material. Another, of course, is because of such an interaction there is a you can say there is a photon to phonon conversion. Okay, so photon to phonon. So there is a bond vibration aspect which comes in on the surface, and so therefore there is a rise in temperature, and there is obviously, if suddenly a portion rises in its temperature, there is going to be heat conduction across the surface, and this would lead to various phenomena like melting, vaporization, ablation on the material surface. So the interaction of the laser beam with the work material is really of the thermo-optic kind, as I told you here, photon to phonon conversion. And obviously when we are talking about a beam of light, there is the question of reflection, and surface should be designed in a manner so that there is not much reflectance of the laser light, because if this happens then we lose quite a bit of laser power. Already laser power overall, if we look at, let's say, solid state lasers particularly, are not very well to do. So therefore, and also they are very slow. Okay, so reflected power is a major issue in all the laser machining processes, and it is obvious that the work surface should not reflect back too much of the incident energy. So if supposing I0 intensity falls on the surface of a solid, by the Beer-Lambert's law, as a function of depth, you have a changing intensity of the material which is dependent on the molar absorptivity coefficient of the material here, mu. This is highly dependent, of course, on the wavelength that we are using. Typically the wavelength doesn't change much when we are talking about a single source laser. It's more or less at the same wavelength that we are operating, so we don't really consider this aspect of the variation of mu with respect to wavelength. Okay, but definitely there is a substantial portion of drop in intensity because of the absorption by the material, and it goes by the expression I0, the surface intensity times of e to the power of minus mu z. Okay, Iz denotes the light intensity at a depth z, and mu is the absorption coefficient in this particular area. So you have an incident beam on a workpiece surface, you have a beam intensity I0, and then there is an IZ intensity which is at a certain depth Z from the surface, work surface, and because of this absorption the material gets heated up and obviously eventually melted and vaporized. So let's now try to model this whole thing by looking at one-dimensional analysis and looking at a heat source that the laser would typically formulate on the surface. So we will perform a one-dimensional analysis by assuming that the beam spot diameter is larger than the depth of penetration. In other words, we are talking about a shallow hole, okay, where the diameter of the hole is very, very high, and this depth here is not as high as the diameter. So if we assume that the thermal properties like conductivity, specific heat, etc. remain unaffected by the temperature change, and also assume an uniform heat flux at the surface of a semi-infinite body So then we can write the one-dimensional heat conduction equation as the following. So you can write this del 2 theta, theta is the temperature, as a function of the depth z and time t by del z2 minus 1 by alpha del theta zt by del t equals 0. Obviously alpha is the thermal diffusivity ratio between the conductivity and the volume specific heat. Theta is the temperature, and we apply the following boundary conditions. So the boundary conditions applied are that at time t equal to 0, when the heat flux has just started, the temperature of the body theta is equal to 0. Similarly, at z equal to 0, that means at the surface here, right about in this particular thing here, you have the temperature gradient d theta by dz really dependent on 1 by K, the heat flux HT per unit area. Okay. So with these boundaries and this PD, one-dimensional PD for solution of the temperature, if we were to investigate the solutions, it would come out as theta zt equals twice h by k root over alpha t by pi exponential minus z square by twice alpha t minus of z by 2 times of the error function of z divided by twice root of alpha t. That is how we will categorize the solution for temperature as a function of z and d. So obviously at z equal to 0, if I outlet z equal to 0 here, we will have the maximum temperature. So theta 0 t, which obviously has to be theta melting for the material to be starting to melt. Okay, so this equals to twice h by k root of alpha t by pi. Obviously this is going to be 0 at z equal to 0, and so is this going to be 0 because there is a z by 2 factor here. So if theta m is the melting temperature of the material, the time required for the surface to reach the melting point, okay, let us assume this to be Tm. So obviously Tm then would be indicated by pi by alpha theta m k by twice h square. This is actually borrowed from the earlier illustration. Theta at 0 t equal to theta m equals twice h by k root of alpha Tm by pi, time for temperature to reach melting point on the surface. So theta m square becomes twice h by k square alpha Tm and by pi, and so therefore this terminology here, right here. So this is an estimate of what is going to be the time for the beam to dwell on a surface so that the theta reaches theta m, or the melting point of the material. Again, for sake of brevity, I am not going into the solutions of the PDE because this is a very standard equation that has been solved in most of the mathematical or mathematics textbooks, and probably if there are questions regarding how this PDE has been arrived at or what is the solution of the PDE, we can discuss it over the portal more so later on. So here we are more concerned with what is going to be the time of machining and things like what is important for a machinist to know for a laser beam to work on a surface. So let's have a numerical design problem here. We have a laser beam with the power intensity of about 10 to the power of 5 watt per millimeter square. It falls on a tungsten sheet. Okay, we need to find out what is the minimum time which is needed for the surface to reach the melting temperature. The melting temperature of the tungsten is about 3400 degrees Celsius. We have the other values related to the surface, including thermal conductivity 2.15 watt per centimeter degree Celsius, the volume specific heat rho c, which is 2.71 joule per centimeter cube degree Celsius, and also we assume that about 10% of the total beam power is absorbed. So having said that, let's now calculate first the alpha value, the thermal diffusivity value. Is the ratio, as I mentioned earlier, between the thermal conductivity K and the volume specific heat rho c, K being 2.15 watt per centimeter degree Celsius, volume specific heat being 2.71 joule per centimeter cube degree Celsius. So we have the thermal diffusivity here as 0.79 centimeter square per second. Let's assume that the beam power in this case is uniform with time. Obviously the heat flux, which is also the, you can say, the energy per unit time or the beam power, okay. The heat flux, which is the energy per unit time per unit area, or in this case, it can be the coupled power density, power density being the power per unit area. So as we all have, as the question says, that the power density in this particular case of the laser beam is about 10 to the power of 7 watt per centimeter square, 10 to the power 5 watt per millimeter square. I'm just converting the units here, okay. So, and the coupling is up to an extent of about only 10%, because as mentioned here that only 10% beam is absorbed, remaining is reflected. So the power, the heat flux H, which would really come, is about 0.1 times of 10 to the power 7 watt per centimeter square, 10 to the power 6 watt per centimeter square, which still is a very large value, very large number. But you can see that most of the power, almost 90%, is lost because of reflection in this case. So if that were the H value, then the time of machining, TM, would really be, and the machining is considered to be a one-shot process, where the whole material would be either vaporized or melted, and there would also be a mechanical impulse which will create spatters of the material, and some redeposition would happen, etc. So the time that we are really wanting machining to happen is really what we are meaning by the time of start of machining, okay. And the start of machining would only happen when theta equal to theta m, the melting point of the material, which is given by the earlier formulation here, Tm equal to pi by alpha times of theta m times of thermal conductivity K by twice H whole square. So in this case, the alpha value being equal to 0.79 centimeter square per second, and theta m obviously is 3400 degrees, K value is 2.15 watt per centimeter degree Celsius, and also the extent of the power here, which is 2 10 to the power of 6 watts per centimeter square. So many seconds of the total time that it would take for the surface temperature to reach the melting point theta m is needed, and so this time is really very, very small. As you can see, it's 0.000053 seconds, okay. So it's very small time that it would take for such a high power density to hit on a surface and create a spot which would necessitate the theta to go to theta m or theta to go to the theta melting. So let's this is only a case where we are talking about a semi-infinite surface. Our actual laser beams are circular in nature, and you really cannot anymore treat the surface to be a semi-infinite, or the surface to be too big for the heat flux to be almost infinite. So these are all only assumptions, and on a realistic level it is really the beam which is having a certain circularity which is into question. Most of the laser beams are focused on circular spot sizes, and so let's look at how this equation would change, or how the formulation would change for a case where we have a circular spot into picture and the surface no longer semi-infinite. Equation obviously would be equation of one-dimensional heat transfer would be del 2 theta zt by del z2 minus 1 by alpha del theta zt by del t equals to 0, and the boundary conditions become theta z0 equals 0 and del theta 0t by del z equals minus ht by k pi d square by 4 times t. So ht is really the you can say it's the power or the quantity of heat. So heat energy as a function of time coming on the surface by the circular spot, and this could be treated as a constant, which we'll see later when we try to evaluate the solutions. And you can basically say that the thermal gradient d theta by dz at a point on the surface when z is equal to 0 as a function of time is really dependent on how much energy the surface is getting per unit area. Okay, so this pi d square by 4 is basically representative of a circular area of diameter d, and time t is basically the quantum of time it takes for the during which the heat energy is being supplied to the circular spot by the lasing source or the laser power, a laser source. So in a way it is a Fourier's equation or a one-dimensional heat conduction, which talks about what is going to happen on the surface because of a constant heat energy addition to the surface, or maybe an energy which varies with a function of time on the surface. So this is energy per unit area, per unit conductivity, per unit time, which is equal to the temperature gradient. So having said that, the solutions under these boundary conditions, again I am not going to really solve the whole one-dimensional condition, heat transfer here. It's a standard solution with the boundary conditions that have been indicated. So the solutions to this equation becomes theta zt equals twice h root over alpha t by k I ERFC z divided by twice root alpha t minus of again I ERFC root of z square plus d square by 4 divided by twice root over alpha t, where this IRFC is only a representation of the error function in general, represented by 1 by root of pi e to the power minus zeta square minus zeta ERFC zeta, where ERFC zeta is again represented as 1 minus ERFC zeta. So it's only a representation. You know that the error function is a numerical integral of any value. Zeta is given by twice root of pi divided by root of pi 0 to zeta e to the power of minus x square dx. Okay, so having said that, we are trying to find out a certain representation here, ERFCC of zeta, through which we can represent this. So this is really how the temperature distribution happens on the surface of a workpiece if there is a circular spot, okay, because of the lasing on the surface. So with this I would like to close today's module, but we'll investigate this more on the more so on a later module, where we talk about a circular spot and actually couple energy and try to see if we can calculate or estimate the depth of melting temperature and what is going to be the zone and extent up to which the theta is equal to theta m, so that we could construct the zone of machining for a laser spot. So with this I would like to end today's module. Thank you again for being with me, and I will see you soon in module 39. Thanks. Bye bye.